Today we're going to be doing the first part of section 5.1, and we're going to be talking about increasing and decreasing functions and how the derivative relates to that. Now, just a review from honors pre-calculus, when we're looking at functions, how do we know if they're increasing or decreasing? Well, if x is increasing, y is increasing, then you have an increasing function. And if x is increasing and y is decreasing, then you have a decreasing function. And so when you look at a through f, which of these are increasing and which of these are decreasing, pause this now and write it down and then see if you get it right. So for a, as x is increasing, y is also increasing, and so that one is increasing. Same thing for b, as x is increasing, y is increasing. And for c, same thing, x is increasing, y is also getting bigger. Now when we get to d, as x is increasing, y is actually getting smaller, so that's a decreasing function. Same for e. And f, as x is increasing, y is also decreasing. So increasing, 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 decreasing, decreasing, decreasing. What is the function graphed in figure 3? Where is it increasing and where is it decreasing? And so we're going to write this in interval notation. And so if we look at this first purple piece, it increases until we get to -4. And so for the purple piece, we would say that it's increasing. And I have to write with my finger on my computer, so it's a little bit challenging, kind of like if you have a broken wrist. So as x is increasing, it's going from -infinity to -4. And we're going to put a hard bracket there. Now, I'm not going to be real picky on the hard bracket and the soft bracket. There's actually a big debate about that right now in the calculus community. And then if we look at where it's increasing again, and I'm going to do all of the increasing intervals in purple, we have that it's increasing from 4 to 6. Now, if we look at the decreasing intervals, and we will do these in red, we have that it's decreasing here, and then we also have that it's decreasing here. And so from -4 to 0, and then it's also decreasing from 6 to infinity. And you will always put a soft bracket with infinity, as always. And then we have between 0 and 4, it's neither increasing nor decreasing. And we're going to look at how the derivative relates to increasing and decreasing parts of functions. So when we look at figure 4, imagine this were a roller coaster, and we think about the tangent lines, which are, remember, the slope of the tangent lines is the derivative or the rate of change right there. And so if we're looking at this first little red piece right here, anywhere on that red piece that we were to draw a tangent line, the tangent line would have a positive slope. And so that first derivative, if it's positive, in other words, if the slope of that line is positive for the first derivative, you have an increasing function on that interval. And so you look at the little roller coaster carts, and they're headed uphill from here, and so it's an increasing function there, and the derivative is going to be positive. And then it levels out for a split second right at the top, and then you're facing downhill, and you have a decreasing function. Well, what's going to be the sign of this first derivative on this little green piece where it's decreasing? Well, on that green piece, if I were to draw a tangent line at any one of those points, that tangent line would have a negative slope. And so if the first derivative is negative, your function is decreasing. And then this little car levels off again right here, but then it starts increasing again. And it increases up until this maximum right here and levels off, and then it starts decreasing again. And so you think about drawing the tangent lines, or where that instantaneous rate of change is occurring, and the slope of those tangent lines determines if that function is increasing or decreasing. So we're actually going to be testing for intervals where f of x is increasing or decreasing. So suppose a function has a derivative at each point in an open interval. then f prime of x, so the derivative of x, if it's greater than 0, then the function is increasing on that interval. If f prime of x, or the derivative, is less than 0, then the function is decreasing on that interval. And if f prime of x equals 0, then f is constant on the interval. And the other thing we need to look at as we're doing these is critical numbers. And so the critical numbers for a function of f are those numbers c in the domain of the function for which the derivative of c equals 0, or the derivative of c doesn't exist. And so these are the critical points that we're going to be looking for to determine where a function is increasing or decreasing without using your calculator. So to apply this test, we first need to locate the critical numbers for f on a number line, as well as any points where f is undefined. So we're looking for critical numbers and undefined points of the function. These points are going to determine several open intervals. Then we're going to choose a value of x in each interval and determine if the derivative is greater than 0 or the derivative is less than 0. And then we'll use the test on the previous page to decide if the function is increasing or decreasing on that interval. So if we want to, hold on, I think an example is missing. Okay, I found the example. So if we want to determine the intervals on which the function is increasing or decreasing, we're actually going to do that by first finding the first derivative of it. So let's find f prime of x, which is going to be 3x squared plus 6x minus 9. And so to find those critical points, we need to figure out where the derivative is equal to 0 or where the derivative is undefined. Well, there's no points on which this is undefined, but we can factor this. And if we factor this, we get that it's 3 times the quantity x plus 3 times x minus 1. Now I did that quickly because this isn't a lesson on factoring. And so now we know that we have critical points at -3 and 1. So we're going to test on this interval for -3 and 1. And so basically I'm going to draw a number line. And I'm going to put -3 on it. Here's 0, here's 1. And so we basically have 3 places in this interval we need to check to see if the function is increasing and decreasing. And we're just going to pick random values in each one of these intervals. And I'll even put a little smiley face to show where these, create a pen, I want a smiley face, critical value, critical value. So when I test the purple area, I'm just going to plug -4 into the first derivative. And so when I do that, I want a normal pen now. Hold on. Pen. F prime of -4 is equal to 15. So it's positive. And so what that means is that the function is going to be increasing in that entire purple interval. So from -infinity to -3, the function is going to be increasing. And now we're going to test a really easy point in the red interval, and we're going to look at f prime, and I'm going to pick 0 because 0 is always so easy to test. And so when I plug in 0 to f prime of x, we get that it's -9. And so what that tells us about the function is that it's going to be decreasing. And then when I look at the blue area, and I can test any point in the blue area, and I'm going to pick the easiest one that I can, I'm going to do f of 2. And that equals 15. And so the actual function is going to be increasing on that interval. Now what this allows us to do is, if we didn't have our handy dandy graphing calculators, this allows us to figure out where some easy points are that we could use to graph this function. And so we're actually going to plug in those critical points to our original function. And so we're going to find f of -3 and f of 1. And so let's see, f of -3 And so we go back to the original function, which is x cubed plus 3x squared minus 9x plus 4. And I'm not actually going to show all of the algebra to this, but when you plug in negative 3, you get 31. And when you plug in 1 to the original function, you get an output of negative 1. And so I'm going to go ahead and put these points on our graph. So we have negative 3, 31. This is not going to be real accurate here, but I'm trying. Negative 3, 31. And then we have 1, negative 1. So that's right here. Well, relatively close to that. It's hard to get exact with my finger. So when I look at the purple piece, what I know is that this function is increasing from negative infinity to 3. And so for that purple piece, and I'm just kind of sketching this, we know that it's increasing, and so our function is increasing there. And then for the red piece, we know it's decreasing between negative 3 and 1, so we can go down to here. And then we know that it's increasing again from negative 1 to infinity. So I actually should have curved that a little bit. And so you have a maximum point at negative 3, 31, and you have a minimum point at 1, negative 1, and then it heads back up. And so it gives you a nice way to be able to sketch that function. Wherever that derivative is equal to 0 is going to be a maximum or a minimum of the original function. So let's look at another one. Find the critical numbers and decide where the function is increasing and decreasing if f of x equals x minus 1 to the 2/3. Well, when I look at the original function, there is no place where x is going to be undefined. So we can move on from there, and now we're going to go straight to the derivative. So f prime of x is going to be 2/3 times x minus 1 to the negative 1/3. And so I'm going to rewrite that with that in the denominator. So we get 2 over 3 times the cube root of x minus 1. So for our derivative, we have a denominator now, and now we look at, is there any way to make the derivative equal to 0? Well, no, there's not. But is there any place where the derivative is undefined? And there is. So the derivative is undefined where x is 1. And so because 1 is in the domain of the original function, but it's an undefined point of the derivative, 1 is our only critical point. So now we're going to show on the number line our critical point, which is simply 1, and I'll put a little happy face on that. Critical point. And so we only have 2 intervals that we need to test here. We need to test from negative infinity to 1, and then we need to test from 1 to infinity. And so I'll make this interval red, and I'll make this interval green. And so when I plug in these critical points to the derivative, let's just do 0. So let's find, for the red piece, let's do f prime of 0, because we can pick any number that's in that interval. And all we're testing is to see if that derivative is positive or negative. So f prime of 0 is going to be negative 2/3. So in this case, the derivative is decreasing. And now for the green interval, we're going to test another easy point. So we're going to do f prime of 2. And when we plug that in, we get positive 2/3. And so in the case of the green zone, it's increasing. And so to find some points on this original function without using our graphing calculator, the first thing we're going to do is we're going to look at what's happening in the function when we plug in that critical point, because it's not undefined there. And so when we plug in f of 1, the output is 0. Okay, sorry, I had a bad graph there that I wanted to change. And let's go ahead and plug in f of 0, just to get another good point on the actual function. So when we plug in f of 0, we get negative 1 to the 1/3. So that's going to be negative 2/3. And when we plug in f of 2, we get 2/3. Oh, sorry, this is positive 2/3 as well. I was actually accidentally looking at the derivative. And so just putting these points on the graph, we have a point here, and then we're going to go to 0, oh, sorry, 1, 0, and we're going to go to 0, 2/3, and 2, 2/3. So we have a little cusp on this function when we graph it. We know that it's decreasing in this red zone here, and it is, and in this case it's increasing here, and you can certainly check that on your calculator. And we have this cusp at 1, 0, and that's a critical point that occurred in the function. And so there's a good sketch of the graph based on the first derivative. So let's do one more, and then you can start in on your homework. And so find the intervals for which the following function increases and decreases and graph the function. Well, first we're going to look at restrictions on the original function. And so in the original function, x can't be negative 1. So we know we have that restriction. Now when I find the derivative of f of x, so you have to use the quotient rule. And when I do that, and I'm not actually going to show the work on that because this isn't a lesson on how to do the quotient rule. You're going to get 2 over x plus 1 squared. And if you want to pause it right now and make sure that's what you get, you are welcome to do that. Now, as we're looking at graphing this function, we're still going to apply our old rules, and we're going to put our asymptote at x equals negative 1. Okay, that was supposed to be straighter than that. Hold on. Let me go to the handy-dandy line function. So we're going to have an asymptote at x equals negative 1. That is so much better. And we're also going to have a horizontal asymptote. Remember, when you do the limit as, oops. So to find the horizontal asymptote, you do the limit as x approaches infinity, and you divide by the highest degree, so you get 1 minus 1 over x over 1 plus 1 over x, and that simplifies to 1. And so we have a horizontal asymptote at y equals 1. Now this is a blast from the past, but things continue to come up in math, so we will put that horizontal asymptote here. So we have the framework for our function. Now, the critical points, if we look at where the derivative can equal 0, there's no place where it can equal 0, but we do have a place where it would be undefined, and that is where x equals negative 1. Now, careful, because we want to say this is a critical point, but if that value is not included in the domain, it's technically not considered to be a critical point. We got that restriction from our original domain of the original function, so it isn't considered a critical point. However, it is the intervals on which we are going to test to see where our function is increasing and decreasing. So we're going to look at two different parts of the domain. We're going to look at where the derivative is in this first region, and I'm going to do that in red. So let's test a point there. So we're going to test f of negative 2. And so negative 2 plus 1 is negative 1. 2 over, we square that, it's positive. So f of negative 2 is going to give us 2. Sorry, that's f prime. And then let's go ahead and test this region here, and we're going to plug in 0 for that. So let's do f prime of 0. So we know that this one is increasing, from that point we just tested. And when we plug in 0, we also get that it's 2. So we know that it's also increasing on this interval. So now let's figure out, when we plug these points into our original function, what we get. And so if I go to our original function and I plug in f of -2, then we're going to get -2 minus 1 is -3, over -2 plus 1 is -1. So we get the point -2, 3. And we know it's increasing. So what this is showing me is we have these asymptotes, we know it's increasing, and so it's going to be doing that for that branch of it. When we test a point in the other region, so we're going to test f of 0, and we're going to get -1 for that. So we have that 0, -1 is in this function, and it's increasing. So as x is getting bigger, y is getting bigger, and so that gives us the other branch of the function. So that's the general idea of today, is using the first derivative in order to figure out where a function is increasing and decreasing, and really focus on finding those critical points based on the first derivative and testing those intervals to see where it's increasing and decreasing. And there is your homework right here. See, things magically appear when I do videos. Wow, that is really hard to circle. Good luck.